Well, good evening. Welcome to Space Oddities. Thank you very much for joining us on this Monday morning. Monday evening. I'm getting confused with my own time zone here. How is everybody out there in YouTube land? Okay. Thank you very much for joining us. Thank you to those of you who bought us coffees last week. As always, much appreciated. And we hope you're busy buying your Space Oddities T-shirts and hoodies. Details are in the description of the video if you'd like to buy those. So we have a special guest tonight, the Angry Astronaut, or rather, we were meant to have a special guest tonight, the Angry Astronaut, but I'm afraid he's failed to materialize this evening. So we don't know where he is. So apologies for that, but that's out of our control, really. So we will press on regardless. So we're hoping that he's going to make an appearance at some point during the show. But as of yet, he hasn't. So I think what we'll do, the first thing we'll do, would like to welcome back Rachel, who's been obviously rather busy with little Isaac of late. And Rachel's come back tonight, especially to do the viewers gallery for us this week. So Rachel, would you like to tell us what's going on with the gallery then?
I will indeed. We've got some good selection this week. As always, the quality keeps getting better and better. But our regular Jerry has sent in the Crescent Nebula in the Cygnus with his normal setup.
Oh, wow.
And again, he always has such a lovely palette. I love to wait to see what Jerry sends in because it's you really feel like that crescent in the middle is really glowing, isn't it?
It is, isn't it? It's amazing.
Which is...
You did a similar image, didn't you?
Yeah, I mean, do you know what? I never used to want to do this one because I said it was like the nebula I hated the most. I think it was really ugly, but then I did it, and now I do like it. I don't think it's so
like
brain-like, isn't it?
Yeah, it does look like a floating brain.
And I don't understand why it's the crescent.
No, that's strange.
But
it is lovely. So well done.
Very
that's
lovely,
a great image.
Jerry.
Well done, Jerry.
Then we have some entries from Kev, who's done the sun. So this one's one of the active regions. He's put at the bottom near the western limb and a bit of prom action.
Beautiful.
Yeah, that's spectacular. Yeah.
That's well done, Kev. Look at that.
You can just feel the texture from the image.
Yeah, it's amazing. It's truly amazing.
So
Alpha. Yeah.
So,
Another winner, Kev.
Always a high standard. And then we've got some more, the sun in white light this time. And he says this is the close-up of the eastern active regions, and can you see the scary face? I think I can hear.
Oh, yes.
Is it on the bottom right, the first?
Yeah, the first of the group on the right, yeah.
It almost looks like a howling baboon to me.
It does, doesn't it? It looks a bit like Einstein to me.
Yeah.
So definitely Einsteinian. There we are.
There's the big version, look.
Ah, good. Ooh. That's nice.
That's lovely. Another winner, Kev. Fantastic.
And for the hat trick, we've got another one by Kev. He's been busy. And this is a image again of the sun with the hydrogen alpha disk. Which...
Wow.
Yeah.
Very good.
For itself, there's no words I can say.
Yeah, what can you say? It's a perfect image. Well done, Kev.
So yeah, really.
It's got everything there, hasn't it?
Yes,
everything.
Yeah,
beautiful.
Amazing.
Then we're creeping over to Mr. Rog.
Who?
Roger the Dodger.
Oh no!
I mean, I've had to come back just to stop him putting all of his images in. I've had to put a stop to this. So obviously Roger's done a Hubble palette with this. He's got 4.5 hours of HJ, 2.5 on sulfur, and 2.5 on the oxygen.
Wow.
And here is your finished image, Roger.
Well, that's my first completed narrowband.
Nice.
Very well done.
I'm now imaging elsewhere in Cygnus.
I say, when did you do the oxygen? Because that normally gets absolutely battered by the moon. We don't ever image oxygen when the moon is like more than sort of a half. So that's really well done.
I did that when it was when the moon was just almost new. So that's why.
Yeah.
Anyway,
very good collection. Then Chris O'Riordan sent in the Cave Nebula, and I do really like this target. I think she's really interesting. And this one's in Cepheus. But again, he said he's struggling to see where the cave is. It looks nothing like its name suggests. Yeah, I don't know why it's called the Cave Nebula.
No.
This is a total of a 9-hour integration. So you can put in the hours for this one.
Beautiful.
Very nice.
Absolutely beautiful.
And I believe that concludes our gallery this week.
Ooh.
Thank you very much, Rachel. That's absolutely
short
brilliant.
but sweet, lovely images.
Yeah, they are. They are absolutely lovely. Just while we're on the subject of what's going on, don't forget that we've got the peak of the Perseids meteor shower coming up the night of the 12th and 13th. Always worth going out. Of course, you can see the Perseids now. The shower has started, but the peak night will be overnight on the 12th and 13th, and in the early hours of the 13th. So worth staying up for.
I think our lovely Kath, she's been taking some pictures, and she thought she might have caught one of the Perseids, I think, last night or the night before.
Yeah. And I remember when I used to go to Astro Camp in East Sussex, one year we stayed up throughout the whole of the night on the peak night, and we counted 630 odd meteors.
Oh, wow.
Oh, excellent. That's a good night.
I've
just noticed that Ian, I think he's been smoking the banana leaves again.
Not again.
He says there's a bear's face at the bottom of the Cave Nebula. So it's probably hibernating.
Oh, right.
One of Mike, who Rachel knows, he managed with one of his meteor cams caught 135 meteors last night.
Last night?
Wow.
Just last night.
Wow. So you see,
I just wish I could keep some clear sky.
It's and this year is going to be very unusual because there's no moon this year.
That's
There
right.
is
Yeah.
no moon.
You know, as long as you've got a clear sky, you will see some Perseids. There's no doubt about it. So look to the east after dark. That's the direction of Perseus, and that's where the radiant is. And you, of course, you know, as Daz and I were saying recently, in attempts to photograph them, you point your camera at one point of the sky, and you've no sooner got the shutter open than a meteor appears in another part of the sky. So you move your camera, and then the same thing happens, and that's the only way I've ever managed to get a Perseid on film is to actually light that completely by chance and not coming from the radiant.
That's why I've now got 3 cameras.
Yeah. Also, Andy, it's good to just get a comfortable jet deck chair and lie back and look into that direction, and then
if you get your
I mean,
if you get your cameras going on repeat, then you can just sit back on the. I got a hammock. My meteorite is a hammock, and I just lay there and just observe the sky, and the rest I'll catch with the cameras. And like I said, as Andy said, they tend to be uncooperative.
Yeah.
So I have 3 covering the bits of sky that I can actually see. So
I think if you learn to sit and relax your eyes instead of looking in, like focusing on a point, you can get your eyes to that sort of almost using the peripheral, and you seem to take more in. You sort of
try not to fall asleep.
That's right.
Sorry, I have a screaming alarm clock that wakes up every 2 hours.
Yes, that's true.
He doesn't let me sleep.
No.
Yeah, so, you know, don't worry too much about trying to photograph and just enjoy the show. Relax. Pour yourself a stiff one. Relax. Don't forget anti-mosquito cream, because that's kind of essential. Well, it certainly is here. So make sure you're well protected against mosquitoes, and just enjoy the show, because sometimes it really is like a firework display. And we hope for lots of bright fireballs this year, as ever. I've only ever seen 2 really bright fireballs during a Perseids peak night, but they do tend to be very bright. And you know a fireball because they are very bright, and they travel relatively slowly across the sky. And you're talking about a piece of rock that's usually no bigger than your fist, but these are a lot bigger than sort of grain of sand sized meteors that comprise most of the Perseids, or any meteor shower for that matter. So let's hope we have a productive year for the Perseus. If you do manage to get any shots of Perseid meteors, of course, and mail them into the gallery. We'd love to see them. spaceodditieslive@gmail.com is the address, as always, spaceodditieslive@gmail.com. And in terms of the gallery, I am actually building the Space Oddities website at the moment, and we are going to include the readers gallery or the viewers gallery on the website, so you'll be able to direct your friends and family to seeing your page, your photos on the web. If any of you who take photos for us regularly, like Kev and Jerry and others, if you have any objection to putting your photos in our gallery on the website, then please send us an email and let us know. Otherwise, we'll sort of transplant your images to the website. But if you don't mind having your image in our gallery on the website, then we'll do that. Won't be ready yet. I shouldn't think it'll be ready till the autumn. But anyway, that's what we're planning, to have the viewers gallery on the website as well as on our publications. So there we are. Okay. So Rachel, no, can't hear anything. So no, Isaac is being cooperatively quiet. So we've got our next door neighbours. They've just had a baby, and I keep thinking it's a cat all day, and I keep saying bloody cat, and it turns out to be their baby crying. He is crying a lot. I will tell you. Not like our lovely Chloe, who never cried at all when she was a baby. I say that to my wife, and she nearly hits me. She said, "That's because you slept through it, and I had to get up and deal with it." And I'd be saying to her, "Oh, Chloe never cried." So my wife said, "You slept through it.
Never woke me up once," did you say?
So there we are. All right then, let's move on. Lou, you're going to tell us a little bit about sunspots, I believe.
Yes. Here we are, very close to solar maximum, and it appears that solar maximum is going to occur a little earlier than we thought, perhaps by the end of the year, perhaps the first quarter of next year. And of course, this is a time where there's a lot of solar activity, a lot of coronal mass ejections and flares, sunspots galore, and if you're living in the right places, aurora, not to mention the threat to astronauts, but we won't go there just yet. So we thought it would be good to talk about the sun a little bit. And it turns out that you can understand an awful lot about the sun if you just understand sunspots. Okay, so we're going to talk about the sun today, and this may be a little bit long. We may have to cut this and turn it into a two-parter, but let's give it a go. Let's see where we end up here. Okay, so here's the sun that you might expect to see if you have a small backyard telescope with an appropriate solar filter. That's our disclaimer, with an appropriate solar filter. And the sun will look different colors depending on the filter. And Daz already kind of walked us through how nobody really knows what color the sun is. There are different correct answers. But one of the things that you can see in this image is that the edges of the sun are dark, right? And this is actually real. This is called limb darkening. And it has to do with the fact that the sun is gaseous. And so you can see through parts of it at different depths. And some SOME light gets through at the upper regions and less light as you move down. So this is actually a real image. And if you look on the bottom, you can see a tiny sunspot there. Okay, and this is we've only understood this for about 400 years, when Galileo saw sunspots on the sun, and he said, there are spots on the sun, and the church said, no way, there are no spots on the sun is pure and pristine. And Galileo proved them wrong, which probably wasn't a good thing to do, but
dangerous thing to do.
The rest is history, as they say.
Yeah.
Here's a little bit better image of the sun. Again, this is in what we call white light. In other words, all the colors of the spectrum that our eyes can see kind of mixed together to produce a white image. And so now we can really see some sunspots. And you'll notice that they have structure. They have different densities. There's a dark inner portion and a lighter outer portion to these sunspots. You might even notice that they tend to occur in pairs. Well, this is all very important information because it helps us understand sunspots. And we're gonna figure out why all this is true in just a few minutes. I think this was supposed to be a video, actually. So I'm not sure what to do with this. I think I'll just move on because it doesn't do what I want it to do.
The sun never does.
It does, yes. They're like comets or cats.
Or Perseids.
Here we see 6 images of the sun, right? And these are 6 perfectly good images that all look completely different. And most of the reason for this is that the sun and all other objects in the universe look very different depending on the wavelength of light that we use to view them in. In the upper left, we have X-rays. The sun in X-ray, this is taken, of course, above the atmosphere because X-rays are absorbed by our atmosphere, which is a really good thing. And so we're seeing very hot regions of the sun. We're seeing into the corona of the sun that can reach 1.5 million degrees centigrade. Further just to its right in the blue there, by the way, these are colors we made up because we can't see these colors. We see the sun in ultraviolet light, again, from above the atmosphere because very, very tiny amounts of UV radiation make it to the surface of the Earth. So here we're seeing a little bit lower down into the atmosphere, a little cooler. We see a white light image, or V for visual image, on the far upper right. A hydrogen alpha image down below. This is just a very specific form, very restricted format of red light that deals with a transition of electrons in the hydrogen atom. And then infrared and radio. And so the point here is that objects in space look different depending on the wavelength of light that you're using to view them in. In fact, objects on the Earth look different. Well, here's an image of the sun, right? If you're an amateur astronomer, perhaps even if you're not, this is an image of the sun with the moon right in front of the sun, causing a total solar eclipse. So you see the moon is very dark here, and on the outside you see the very soft, tenuous solar corona that you can't see normally because the sun, the photosphere of the sun is just too bright. But look carefully. You can see some structure in the corona. And that structure is reflective, is evidence of the sun's global magnetic field. The particles in the solar corona, many of them are charged particles, and so they are attracted to magnetic field lines. And that's what you see here. The corona is glowing, being attracted to the field lines, and so that gives us that allows us to see some of the sun's magnetic field. That's important for our understanding of the sun and sunspots. So hang on to that. So I've given a lot of talks about the sun, and sometimes they just get so esoteric. And so it occurred to me one day that if you just understand 5 things about sunspots, you can basically understand the entire sun and how it works. So 5 things about sunspots. They're dark, as we have seen. They're cool. So I have Joe Cool on the right-hand side there to remind us. They're highly magnetic. They're associated with solar storms, coronal mass ejections, and flares. And the number one thing to understand about sunspots is they come and go in cycles. So you have the bicycle down there for the,
Don't give up your day job.
Remind us. So we'll just go on for now. Okay. When we look carefully at sunspots, and this bottom image, by the way, is a ground-based image from a solar observatory, maybe National Solar Observatory, we see that it has structure. It has a dark inner portion and a lighter outer portion. The umbra is the inner portion, the penumbra is the outer portion. And outside of that, we see the bubbling, I'll call it the surface of the sun. It's the what we generally call the surface of the sun, the photosphere, as heat is rising, the sun trying to equilibrate with its surroundings, get rid of its heat that's being generated in the core. So sunspots definitely have structure, and we're going to talk about why. Here's another image of a sunspot up close, just like the one we saw before. The inner darker part, the umbra, is cooler than the surrounding area, the penumbra, which is also cooler than the surface of the sun. Surface of the sun, let's see, we have mostly UK people. So do you guys use centigrade, Fahrenheit, Kelvin? What do you use? It's about 6,000 degrees centigrade. And the inner portion of sunspots may be 3,500, 4,000 degrees centigrade, something like that. And we're going to learn why they're cooler. Well, this was supposed to be a video too. Heck with it. Let's move on. Okay. We have very good evidence now from the physics and from observations, especially a field called helioseismology, which is looking at how the sun rings as sound waves propagate through it, that we can look at the sun as being composed, at least from the photosphere down, into three parts: the core, the radiative zone, and the convective zone. In the core, where temperatures can reach 15 million degrees centigrade, centigrade Kelvin doesn't matter at that level, we have fusion taking place where two protons are fired together at very high speeds because of the high pressure and temperature to bond together, to bypass that repelling force and actually fuse together. This cannot happen in classical mechanics. And all of the physics that we learned in up to the 1800s, this cannot happen. But we know now through quantum physics that this does happen. So that produces the gamma ray photons that begin in the core of the sun. They migrate out into a region called the radiative zone where they are scattered by electrons, free electrons in that zone. And they're scattered so much, just kind of like a drunk man's walk, if you've heard of that, that it takes on average, statistically, about 100,000 years for that single gamma ray photon to get out of that radiative zone of the sun. 100,000 years. As you move out from the center, it gets cooler and cooler and cooler. And so all of a sudden, you can form atoms. You can have electrons kind of hanging on to nuclei. And as things cool, the most effective means of heat transport is convection. And so they form these convective cells that rotate. And those gamma ray photons hitch a ride on those convective cells, reach the surface of the sun, and then it's 8 1/3 minutes to get to the Earth. Okay. We know sunspots are dark. I've told you they're magnetic, but how do we know? One of the ways we know is that we see a quality when we look at the spectra of sunspots. We see a quality called Zeeman line splitting. Zeeman line splitting. And it means that spectral lines in the presence of very powerful magnetic fields will split into three parts. And we see this visually here of a spectrum where a spectral line has split. That is observational evidence that these sunspots are very magnetic. And the reason they're magnetic is that the sun rotates. But it doesn't rotate like a solid sphere. It rotates like a kind of gloppy, gas. And so the equator of the sun rotates once every 27 days or so. And it's rotating faster than the upper and lower latitudes. So the magnetic field of the sun gets dragged around time after time, month after month after month, until it gets really tangled. You might imagine having if you knit, I don't know how many of you knit, but if you have a big piece of yarn and it's all kind of, clumped together, and you throw it in the bottom of your closet, that piece of yarn might have a little piece of yarn sticking up over all the rest of them, just a little piece. And that in the sun would be a sunspot. And since that little loop of magnetic field is looping above the sun, you have one side and the other. You have a north and a south pole. because magnets have north and south poles. There are no magnetic monopoles. So the sun is sunspots are magnetic, and this is really important. Just an image of the sun in ultraviolet light, showing many, many active regions on the sun. You can even see little loops. If you look on the edges of the sun here, you can see little loops of this plasma. And this is the material rising from a sunspot, from one side of a sunspot, and diving back down into the other, because these plasma obey magnetic field lines, just like as we saw before. So why are they cool? They are relatively cool. And the reason is that the magnetic field in the region of these sunspots is pushing down on that gas that's trying to upwell to the surface. Remember the convective zone just under the photosphere? And since they're pushing down on this gas, it can't get out there, so it has to move around the sunspot and emerges on either side of the sunspot. But the sunspot region itself is cool as a result. Now, okay, this is my favorite slide because it has a little equation in it. And it's actually not that hard to understand. It turns out that a small drop in temperature produces a large drop in brightness. So we just said sunspots are cool, relatively cool. In this equation, L is luminosity or brightness, and it equals 4, that's a number, times pi, that's a number, times radius, which is just a number, times sigma, which is a number, times the temperature to the 4th power. So you modify the temperature just a little bit, raise it to the 4th power, and you have a huge change in brightness. And this is why sunspots are so dark, because they're cool. It also turns out that solar storms, and we're seeing a lot of solar storms these days because we're very near solar maximum, solar storms tend to occur around large sunspot regions. Solar flares, which are generally dominated by electromagnetic radiation, and coronal mass ejections, which are dominated by particle radiation, they tend to occur around sunspot regions. So during solar max, we see lots of sunspots, bigger sunspots in general, and more solar storms. No accident. So, what have we learned about sunspots? They're dark. We know why they're dark. They're cool. We know why they're cool. They're magnetic. We've seen evidence of that. They're associated with solar storms, just because I told you. And and they come and go in cycles, but we haven't talked about the cycles yet. Let's see if I have a.
That's fantastic.
Where are we in time? I don't know how to break this up quite.
We've got we're half an hour into the show.
Okay. I wonder if well, you let me know. You have a hook. Andy has the hook. And he will hook it around my neck and drag me off as I wave to screaming fans.
Right. Well, I mean, it's all interesting stuff, Lou. So we would love to see it. So no problem at all. Yes, indeed. Right. Well, thank you for that.
Perhaps we'll carry on next week with the rest of us.
Yeah, we can carry on next week.
Yeah, because I mean, Lou, you mentioned the corona being up to 1.5 million degrees in heat, hotter than the actual surface of the sun. Well, just recently I was reading a paper that they think they may have solved that problem, why the corona is so much hotter. And it was I'm not sure whether it was Betty Colombo or Parker Solar Probe, one of the two.
No, it was the studying solar orbiter.
Oh, okay, then not even the one I was thinking
Europeans always want to take credit. I mean, come on.
For good reason. We just do everything better. That's why.
Of course.
Yeah. What they noticed was that you were talking about these magnetic lines on the surface of the sun, which usually join the spots and all that. But there's also other magnetic activity going on, which gives us the plages, which is the light areas. So there's a lot of magnetic activity going on. But what they found is that it's covered in these little magnetic lines, which apparently are vibrating very rapidly. And they think that this vibration of all these small magnetic filaments is possibly the cause. And like I said, it's possibly, with the sun, we don't know positively, is what's actually heating the actual corona to such a high temperature. And if it's correct, then that's one more nail in the coffin of the mysteries of the sun.
If you remember, Daz, I was showing some images of those last week. And they're like,
oh, of course, yes. Sorry,
no problem. Yeah. They're like little magnetic waves that are traveling rapidly across the surface of the sun, and they think that's what's, as Daz said, that's what's heating the corona.
Now, would these be the elfin waves? That this was the prevailing theory before Parker was launched.
I don't know.
I couldn't tell you offhand. But also, you were talking about the cycle. Of course, we were expecting cycle 25 to reach its maximum on 2025, but because it's the prediction, this is outdoing all the predictions that they've made so far. They expected the solar spot activity to be very low, like the previous cycle 24 was. And they were then, of course, there was also some people that were expanding that. If we go into, what do they call it, a great solar minimum, which could eventually lead to an ice age. Well, that'll sort out our global warming problem.
I have to break in here. We have been laboring under that theory for a long time. The regions of time where there are essentially no sunspots, Maunder minimum and all that, and the ice age that occurred in Europe during the last one, I think the late 1600s. That appears not to be the case any longer. That a more careful review of the data, I was teaching it. But a more careful review of the data suggests that sunspot minima, even prolonged sunspot minima, do not result in mini ice ages as much as we need a mini ice age right now. I don't think that's borne out by the data.
Not from that anyway. Oh, that's a shame.
Yeah, because the second minimum you were talking about, was that the Dalton minimum?
Oh yes, there's
yeah, there was a Dalton. Okay, so that's burst that bubble anyway. But of course, we've got an average of these cycles is 11 years, but they can vary to be as short as 8 years and up to 14 years, I think it was. So the 11 year is an average. And of course, if we're going to go to maximum the end of this year, because the solar spots have appeared a lot more than we were expecting and so much quicker, that because if you see a graph, you can see there's a little hump, and the 25th of 2025 was the maximum. Then it's supposed to come back down again. The actuals, if you look at what the actual sunspots have gone, it's actually above the line and climbing still at this very moment. So if we do go to a maximum at the end of this year, it would be interesting to see whether that means we're going to get a very long decline to a minima to cover sort of like more towards the 11 years, or we're going to have a very short cycle. It's fascinating to see it actually pan out, how it's actually going. So it just goes to show that we really, although we know a lot about the sun, we don't know enough to predict anything at the moment. So it's, as you said, it's very, very interesting.
The problem is that there are two ways that we can make predictions outside of Ouija boards. One is to look at the previous behavior of the sun, right? And we had seen that the solar maximum had been declining over the previous cycles. The other, which would be much more accurate, would be to actually understand the solar cycle why it is the way it is and what drives it. I mean, there's some thinking that gas moves latitudinally and dives down to the tachocline region below the photosphere and all this stuff. And we don't really understand it. But if we understood the physics well, then we would be able to predict with better accuracy. And we just don't yet.
No. I mean, one thing I did forget to mention is we could also have a double peak. Yes. Of maximum. It can start to decline and then pop back up again. So it's fascinating. I find these sunspots and these cycles, and of course, I think it was Ian mentioned it last week when we mentioned the sun, is that at the end of this cycle, the poles will swap. So that's one of the ways we know that the cycles come to an end. And also with your dual sunspots, they've got polarities. They will also swap, and that's how we know we've come to an end of a cycle. But then you've then got supposedly another cycle, and I think really we need to look at not the 11-year cycles, but the 22-year cycles when things have changed, because there has been some predictions that what they call a south lead cycle tends to have have more interaction with us than with solar weather than a north one does. It's just fascinating. I find this so interesting. And if anybody wants to know a little bit about, I mean, Lou's done a wonderful job as regards telling us about the sunspots. If you look at on the YouTube and look at our the presentation, which was does the solar cycles interact with earthquakes and volcanoes on Earth, have a look at that, and that'll give you a brief description of how these cycles work. So
and can I just say as well that sunspots are not unique to the sun. We have actually observed them on the surface of other stars. So we know that they are a common feature of stars, that they are sort of intrinsic, if you like, to the activity of stars. For example, here's one on the surface of, let me just make that a bit bigger, of Zeta Andromedae. You can see three clear, well, astronomers call them star spots, of course, not sunspots, because they're not on the sun, they're on other stars. So these are star spots, and this is another star, big star called Zeta Andromedae. And I think they've imaged them on Betelgeuse, Regulus, and Antares, if I remember right.
Yes.
I mean, as well as sunspots, you've also got to think about coronal holes, which also give us intense space winds. And Kevin here is talking about plages and faculae. There's a lot of things that actually go on the surface of the sun, which all interact, and they all do their own thing. I mean, there's been a couple of this week alone, we've had about 3 or 4 storms come our way from flares and coronal mass ejections. So it's really ramped up at the moment. And if you want to look at this, a website which I've just found recently, it's called solarham.net. Now, if you go to that, you'll be able to look at the sun in different wavelengths, as Lou was pointing out. Every wavelength gives you something different to look at.
What's it called,
and it's solarham.net.
Solarham, as in H-A-M.
H-A-M, yeah.
Okay.
And from there, you can actually link up to NOAA, which is the North American space weather community, or just Google NOAA space weather, and there's one on there called panels. And if you go on the panels, it gives you all these graphs, all these diagrams. And if you go to the actual NOAA site, you can actually watch videos of what's happened in the last few hours and things like that. So and it's all free. So have a look. It's fascinating.
Great.
Yeah, you can spend hours on it. Anyway, I'm waffling now.
So what
sorry.
we'll do now?
Yeah, lovely talk, though. Lovely.
What
talk,
we'll do now? We will move celestial objects a bit closer to home. We'll move from the sun to the moon. Now, the moon has been in the news a lot recently because of supermoons, and the media hype is just getting hysterical every month about these supermoons, and the rat moon or the dog moon or the inside trouser leg moon or whatever it is. It is all media hype. The supermoon happens when we get a full moon, when the moon is closest to the Earth in its orbit. And these are very common, of course. But what you have to remember is that visually, the moon can only appear up to between about 5 and 7% bigger than normal in the sky. And the human eye isn't really that sensitive enough to see that difference anyway. So this is all media hype just to sell copy and column inches, as always. However, we also have the term blue moon. Now, do you know what a blue moon is? So, you may not, but if you don't worry, because Daz is actually going to tell us all about it. So let me just get this set up, Daz, and we will learn all about the blue moon.
The phrase blue moon in modern usage has nothing to do with the actual colour of the moon. Although
you turn it up, Andy.
The moon appearing with a
1 second.
May occur.
1 second. Is it not very loud?
No, it's a bit dull. It was good earlier on.
Okay, just give me 1 second.
Yeah, no worries.
That's a full volume, Daz, I'm afraid.
Okay, then I don't know if let me if you can start it again, then we'll have a listen on the channel, see what's coming out like.
All right. 1 second.
Under certain atmospheric conditions.
Okay, let's try it again then.
The phrase blue moon in modern usage has nothing to do with the actual colour of the moon. Although a visually blue moon, the moon appearing with a bluish tinge, may occur under certain atmospheric conditions. For instance, if volcanic eruptions or wild...
No, it's still quiet, Andy.
Into the
sounds okay from here.
Just the right size to preferentially scatter the red light.
Yeah, it's low on the channel, on the YouTube and that.
That being said,
okay.
A quick quiz. When is the next blue moon?
Right. Well, obviously, we'll if it can't be heard properly, we'll ditch that, and and we'll see if we can re-record the audio so that it's a bit louder. But that is at full volume, so unfortunately, that's the way it is. So there we are. Okay. Well, not to worry. We're going to move on. Sorry about that, viewers, but we'll have to look into that and see if we can improve that for you. So what we'll do now, we will move straight over to Roger. So Roger, what's going on in the night sky this month?
That's better. Right. Okay, so we're now into the first full week proper of August. Well, we're nearly halfway through by the end of the next weekend, but here we go. There's not an awful lot of excitement in the night sky at the moment, but this was what the moon looked like at 3 o'clock this morning. So probably not a dissimilar time to Rachel looking up at the night sky as well. But,
what are you doing up at 3 o'clock photographing the moon?
For goodness sake.
Well, I was out photographing some more objects in the night sky, and then I thought, oh, the moon's up. I better go and photograph that as well. So I eventually went to bed about 5 o'clock this morning. So there we go. Dedication of what happens when you get a clear night sky. And the day before was the sun, funnily enough. A few spots there, but nothing extraordinarily large, but still activity on the go. So that's obviously a white light image. And unlike Mr. Earp, I decided to do some HA as well. And
very nice.
Some of the activity over on the western limb of this part of the sun. So yeah, not too bad.
That's lovely.
That is nice. Lovely.
Readers Gallery Part 2. Okay, so we're getting towards the new moon with the third quarter tomorrow, and an ever waning crescent to follow. And these are what we can expect to see in the night sky during this week at 11 o'clock at night. The only current planet that's available at the moment is Saturn, which is rising, and Jupiter will arise later on in the night. But the sky is dominated near the zenith with the summer triangle. And obviously we've got the galactic core still nicely in the south for any those that still want to image the Milky Way. And there we go. And we've also got Andromeda coming up nicely now. And if you wait long enough, you'll start to see the Pleiades coming up not far after when Jupiter rises. So winter is definitely on its way.
Fantastic. Can't wait to get Jupiter back in the evening sky.
Yeah, well, it won't be far. I mean, Saturn will be at opposition later in this month, but Jupiter will be at opposition in December, which is nice, and it's up at quite a good height. So all the better for Jupiter, but Saturn unfortunately still is quite low in the northern hemisphere for our 51 degree north latitude people. So have to make do. But as you can see on the tomorrow morning wee hours, we've got the moon and Jupiter fairly close together, so that might make an interesting opportunity with the telescope or a wide lens to capture them both at that phase. So look out, Rachel. And then it obviously moves on towards Taurus and the Pleiades and Aldebaran and the Hyades.
Sorry to interrupt, Rog, but Ian's asking, what is the summer triangle? Which stars?
Right, okay, so the summer triangle stars consist of Cygnus, which we've got Deneb at the tail. We've also got Lyra, where we've got Vega, the current brightest star in the night sky, and then Altair in Aquila. So that Altair, Vega, and Deneb, which are the designated triangle for the summer.
Yeah, Simon from Bath Astronomers, he did answer the question, but he said it was Vega, Deeb, and Altair. He corrected it to Deneb.
Okay. As opposed to the winter circle, which is consisting of more stars, 7, I believe. So don't ask me off the top of my head,
but basically, Ian, if you go outside and look straight up, Vega is above your head at the moment. It's that sort of blue-white bright star right above your head. So that's one apex of the triangle.
Yeah.
And then if you look to Cygnus, then
Altair is sort of basically in the east.
Yeah, that's right. Altair in the east. You can't miss it. It's like a big triangle on the sky.
Yeah. Yeah.
So
someone told me just a couple of days ago that there's a spring triangle, which I never heard of.
No, I
heard of that.
No.
Spring triangle. I'll have to take a look.
I expect there is, and probably there's an autumn one as well.
See if we can find 3 stars that make a triangle. That would be interesting.
Okay.
They all make a triangle if you want.
They do. Okay,
Steve.
Wikipedia, it's Arcturus, Spica, and Regulus.
Oh, right.
Okay.
Okay.
Boötes, Virgo, and Leo, respectively.
All right.
So there you are.
Yeah, because Steve's put Deneb is the one of the most distant and luminous objects we can see with our own eyes, over 1,000 light years away. And Simon says don't forget the winter hexagon. I think that's what you meant by the circle, Rog.
I've heard of the winter triangle, not the hexagon.
I've
seen the hexagon.
Yeah.
I'll say we did the hexagon in Roger's quiz, didn't we?
We did.
Oh,
yeah, probably.
By
my easy question quiz.
That one.
Yeah.
By the way, viewers, we are organising another quiz very soon, so keep your eyes open for that. We are going to have another quiz, and Roger's not doing it.
Oh, you're such a spoil sport.
So we will have to work out who's going to do the quiz. Well, you can do another quiz, Roger, as long as you make the questions about 50,000 times easier.
Right, then.
It'll be fine.
Yeah.
Be fine.
Great.
Stephen Hawking would have struggled.
Yeah. We don't want to deprive you of the right to do a quiz, but we'd appreciate some slightly easier questions. There's a lot of head scratching going on that day. A lot of people lost their hair over that.
Yeah, as you can see later in the week, we can see Saturn slowly setting, and we got Jupiter coming up quite nicely, along with Taurus and Orion starting to make its appearance. Ooh,
yeah, and here we are. Rachel gives us the lowdown on the winter hexagon. Which is Rigel, Aldebaran, Capella, Pollux, Procyon, and Sirius. There you are. Thank you, Rachel.
Right. Yeah, Ian's still on the banana leaves.
Dodecagrons.
Right. And as Andy had pointed out earlier, we've got the Perseids, which are still to achieve its maximum, but obviously with a clear sky you can get still quite a lot through the night at the moment, and there's still some Alpha Capricornids and some Delta Aquarids as well, so it could all kick off up in the night sky, providing you've got a clear sky.
Roger, do you?
And at the moment the sun's a bit bright, so just look away from the sun. The sun, the moon.
So we are having fun.
I'll get this astronomy thing worked out.
Who's smoking the banana leaves?
Ian.
Anyway.
Roger, do you know if there's sometimes they predict that particularly dense parts of a swarm will pass the Earth at a certain time. Is there a favored place on Earth to see the Perseids, or is it all kind of?
I think it's just a general thing. It's just where you are when you pass through on the rotation, really.
Okay.
And how lucky you are when you get a period of extreme dust getting through to the atmosphere. So
I think normally, Lou, it's the northern hemisphere that sees the greater peak. It tends to alternate between the US seeing the peak in the hours of darkness and Europe. And I don't know whose turn it is this year, but it seems to be that it does alternate between the peak occurring over the US rather than over Europe.
Okay.
So we will see this year. Yeah, so we might be lucky this year. But I mean, on a good Perseid year, when there is no moon, like there is no moon this year, it really is can be spectacular. So we're just going to lay outside and have a bottle of wine and just watch the show, which is the best way of doing it.
yes,
I agree.
okay, right. On with my presentation. Thank you very much. So we have a new image from the web, and this one has got rather a lot of interesting features, which we have here. This is what they call El Gordo, which is a cluster of hundreds of galaxies, which are only about 6.2 billion years old. So it's quite a young group of galaxies at the moment. And
I mean, it's not politically correct because El Gordo means the fat one. So,
we should call it le plus, the plus one.
Plus one, yeah.
Plus size.
Triple X.
And apparently there's a lot of gravitational lensing going on
Yeah,
in
you
this
can see
area as
that.
well, which you can see in this illustration with a few items highlighted on the fact that they're definitely not performing those shapes normally. So,
yeah, because that as you can see, that you can see gravitational lensing in image B on the right there, and also the A, that again is a gravitational lensed galaxy in the background.
Yeah.
And I think it's called Faux or something. I'm trying to find it. Faux or Faux.
The
I mean, if you cut that image in half, one half looks like a mirror image of the other half.
Yeah, it does. Yeah.
So that's obviously part of the gravitational effect.
Yeah. Also, the web this week has discovered a star being gravitationally lensed by dark matter, which is quite a really significant discovery. I'll report more on that next week when I've had a chance to read up some more about it.
Yes. Okay.
So there we are.
Right.
Okay.
Now I've just got this to.
Oh yes, of course.
Oh yes.
Of course, I was the local BBC station, which is points west where I am. We're asking viewers to watch out for the supermoon of the 1st of August. And I put a picture in which was taken the night before, so it was only 98.7% full. But because the weather was so bad on the 1st of August when it was the supermoon, they decided that they would like to use my image. And at the moment, as of earlier today, there was over 12,000 likes for this picture on the BBC West Facebook group.
Wow.
I was quite pleased about that.
Well done, Roger.
And there was a little article on the actual news which only lasted 20 seconds to say that I'd taken this picture, my name and in Sparkford, and what a stunning picture it was. So,
and Simon says you're now famous in the Southwest, of course.
Yeah,
he was already, Simon. He was
even more so.
Lunchtime.
Yeah,
he's world famous in the Southwest.
Yeah, I'll be signing autographs when I'm helping Simon in his outreach in Bath on Sunday.
Hey,
with a nice picture of the moon.
Make sure you're wearing your T-shirt.
Absolutely, I will actually, if it's forecasting to be right. So
yeah,
I can promote that, no problem.
God, do you mean to tell me you might have a forecast that means it's not T-shirt weather? I can't imagine that living here.
Well, I'll probably have about three layers or 4 layers on top underneath the T-shirt as well.
But that is a smashing image, Roger. So well done.
Okay.
Well done. Rog, can you just pop back to the Hubble image?
I
misnamed that thin pencil-like it's let me get La Flaca, which actually means the thin one. So they've gone both ways, and it says not from La Flaca is another lensed galaxy. Where the researchers examined that galaxy closer, they found a single red giant star that they nickname Quillia, which is the Quinoshus term for star. So there's so much in these images. You can find.
It's going to take years to unpick all of this. Which
I think these. Sorry.
No, I'm going to say this is. You know, astronomers have already from the web got years and years of work ahead of them, analysing all this.
Yeah.
Because you look how many objects are in this one image, and every one is a galaxy. And as you can see, they're all shapes and sizes and whatever. So
Yeah, and in the stars with the spikes on there in the foreground, so that's why we can.
The 2 stars, 3, 4 stars that are there.
Yeah.
That are stars.
But everything else in there is a galaxy.
Yeah, it's fantastic. Yeah. So thank you very much for that, Roger. That's absolutely brilliant, and we will look forward to more news of the night sky from you next week. So there we are. Well, I think that just about brings us to the end of today's show, ladies and gentlemen. And we'd like to thank you very much for being here. We do apologise for the fact that our special guest, the Angry Astronaut, was not able, for whatever reason, to be with us tonight. We don't know why, because last time he had food poisoning, but we're not sure why he couldn't join us tonight. We hope, obviously, that he's okay. So we will try and get him back on for the third time. So leave that with us. Big thank you to Rother Valley Optics for sponsoring Space Oddities. Thank you, guys, at Rother Valley. And thank you to all of us who have supported us as well, obviously. So if you would like to buy us a coffee, all you need to do, as always, is to scan the QR code here. I'll just leave that up for a couple of minutes. Next week is a very special week because if all goes well, we are going to be talking to the astronaut Scott Poteet about him being the pilot of the upcoming Polaris Dawn mission, which is a really interesting space mission coming up in the last quarter of this year. I think it's still set for last quarter, isn't it, Michael?
It is. Scott Poteet is actually on the 21st, not the 14th.
Oh, sorry, yes, of course, I'm getting ahead of myself. But anyway, on the 21st of August.
Yeah, still set for later on this year.
Yes. Yeah. So that's the 21st when you can join us live and put your questions to a real live astronaut, Scott Poteet, and ask him about, well, whatever you'd like to ask him about, really. But the Polaris Dawn mission is set to be a really interesting mission because it will break a lot of new ground. It's going to attempt the furthest orbit from the Earth that's ever been attempted. It's going to feature a spacewalk using brand new spacesuits designed by SpaceX, and that should be really interesting. Lots of medical science going on the mission as well. Lots of experiments.
And communications testing.
And communication testing using lasers. So and also the whole thing is to raise money for St. Jude's Children's Cancer Hospital. So the first mission that was captained by Gerard Isaacman, the billionaire. I think what was the figure? 100.
Oh gosh, it's
two. I think it was about 200 million they raised for St. Jude's. They hope to raise a similar amount or more this time around. So this is a mission well worth supporting. So we'll be talking to Scott Poteet on the 21st of August. Not quite sure what we've got coming up for you next week yet, but we hope you will join us same time, 8 o'clock UK or 3 p.m. EST here on Space Oddities. Thank you so much for being here tonight. Thank you to the panel. Thank you, guys. Thank you for a really informative bit about the sun. Always interesting.
It might be worth mentioning, Andy, that Mark Thompson's doing the launch of his Constellation podcast tonight at 11 o'clock.
Oh, tonight, is it?
Yeah, if you head over to @Astronomy Pod, he's doing a Monday at 11 o'clock. Every Monday he's going to do a stargazing session. So
right. Can you put the address of that in the chat, Rachel?
I will. It's over on Twitter or X, whatever it's called these days.
Mark is an old friend of ours. From our Astro Radio days, and if you remember, he attempted the Guinness World Record for the longest science lecture ever, and he unfortunately didn't make it. But how many hours did he lecture for in the end, Rachel? Do you remember?
It's about 141, I think, or just short of 141.
Yeah,
hours with very little.
On his feet lecturing for 141 hours, but unfortunately didn't break the world record for various reasons. But there we are. Yes. So on Twitter, it's or X, as I suppose we should call it now, @Astronomy Pod, And that's 11 o'clock UK tonight. Mark will be starting his new podcast telling you about the stars and stargazing. So we'll look forward to that. We are going to have Mark on the programme soon to have a chat with him, because it'd be good to catch up with him, and he will be able to tell us all about this new venture. So there we are. So we look forward to seeing Mark as well. All right then, viewers, thank you so much for being here. Have a fantastic week. Take care of yourselves. Look after each other, and we'll see you back on Space Oddities next week. Say goodbye, guys.
Goodbye.
Bye.
Bye. Bye, everyone.
Bye, everyone. Bye.
Keep looking up. Don't forget the Perseids. That's the event coming up on the 12th, 13th of August, the peak night. In the early hours of the morning is the peak. So hope you get to see some meteors.